Okay, good morning. So for today's lecture, we will have one student, Ali, actually told me he would really need 20 minutes. That's fine. We will have 20 minutes. Last 20 minutes, he will give the lecture on the, actually the part is more on the previous, the introduction to network, the network modeling, propagation, that part. Actually, lots of them are like Christos Valoutzos, that part line of work. I think it's very good. We will give him 20 minutes. I also should say, as you can see, we got a few students lining up. We have some students line up later. But in the middle, like the text mining part, we do not have anyone lining up yet. Okay, I hope you can actively volunteer because now you got a lot of ideas on what the course is covering. And you, based on your proposal, you probably already start reading a lot of papers. You can discuss with me if you find some papers you really learn quite a lot, you want to present. It helps the whole class and help you yourself as well. Okay. Plus, it does count as a credit. So I hope we have more people lining up for the text mining and the truth finding and the stream data mining, those sections, because these are very useful, very interesting sessions. I want more people to volunteer to present. Okay. So we will continue our presentation we left last time. Last time we mentioned we studied for heterogeneous information networks. We can do clustering, we can do similarity search, we can do ranking. Now people say, I do have class labels. I may ask experts or myself, can give you some interesting class labels. Can you do the classification for remaining nodes and links? That means if I give you, say, this paper is on database, this paper is on machine learning, and can you say, oh, some researchers actually are database researchers, the other set are machine learning researchers. This is very typical, very natural, thinking. Mingji, she worked out 2 research papers on this issue. One actually called the GNet mine. Last time we mentioned a little. We said the general philosophy of GNet mine is we assume there's some kind of a consistency across the links. That means if your neighbor links, for example, you write papers, your neighbor links are all database links. That means you publish many papers in database. Very likely, okay, because you link to the papers already marked a database, likely these authors are database authors, right? So that's very natural. Why, if you're a machine learning researcher, you publish those papers in database conferences, or you get database papers. So that's one we call consistency assumption. That means if your neighbor links, even in heterogeneous networks, you think about papers, you link to venues. If your neighborhood are all in this class, or majority in this class, likely the consistency means you will carry the similar labels. Okay, so this is a consistency assumption. Based on this consistency assumption, you can propagate the confidence of the class, of the objects belong to a certain class. You can propagate by links. Okay, and her propagation by link just based on the objective function. The philosophy is the 2 neighborhood links, okay, like ij and ji, those links, they share similar class label, or their class label information can be propagated. The difference between the confidence of the class label should be minimized. All right, so that's essentially, you can see you sum up all the links. That means there are many links. You try to get a statistic consensus. If the neighborhood link it's clear, you will get some information. We call these as you may have some kind of smoothness. Of course, we can do some kind of normalization, but overall, the information will be passed across heterogeneous objects. Okay, so that's the general idea of GNetMine. Okay, after this, a year later, you can see this is the 2010. A year later, in 2011, she got another idea, another interesting thinking, which is actually follow Ezhou's rank clustering. Okay, Ezhou's rank clustering general philosophy is not everybody is the same. Even you do the cluster, you're closer to the center of cluster, you have more links, likely your rank will be higher. Okay, if you are higher, you attract you attract many more neighboring things also to the same cluster, so the ranking and the clustering can mutually help each other. Okay. And then she was thinking why this is not the case for classification. Okay. In the past, okay, majority of the game, if you study machine learning classification, you know every object, if you misclassified, your accuracy suffer is exactly the same way. You think about this. If I got, suppose, you think about this, even for the doctors, suppose try to cluster the classification of tissues. Say this one is a cancerous, this one is a healthy one. Okay, you get one tissue wrong, you deduce your accuracy. Okay, so in principle, everybody just the same. But in reality, even you think about publication, the research papers or the authors, okay, some are very, very clear they should belong to this class. Okay, it's very highly ranked. Like I said, Mike Stonebreaker is in database. He last year got Turing Award, so he definitely is a database guy. Okay, you misclassify him to machine learning is very wrong. Okay, so because he ranked very high in the database. But you misclassify a first-year student, got a paper right in the middle, you send to database or send to machine learning. Maybe you send it to the wrong forum, publish it, okay? Or he changes his field, so nothing will happen because it's he just a first-year student. He could be very volatile, right? So that simply says highly ranked objects should play more role in classification, should weight more. Not everybody is the same. It's identical. Okay. So then she worked out, basically say the class membership and the ranking are all statistic distributions. That means the class, you can say, I'm 80%, possibility is in the database, 20% in data mining, it's fine. Okay. You do have distribution. Okay. Then the class membership and ranking both will be mutually enhanced. If you rank high, likely your distribution to this one will be higher or will be more pure. Okay, so with this idea, she basically say ranking and classification, you should define an algorithm. They mutually enhance each other. That simply says, at the very beginning, everybody you do not know, you only know a few labels, you can just let the labels propagate. But later, you should work out which objects, which nodes, probably ranked high in this class. Then this one will weight more, weight high. Okay. So she just draw a picture, says, there are professors, there are teachers, there are students, right? The professor actually will have more links to the surroundings, including linking to the teachers and linking to students. Obviously, this professor maybe in that field should rank higher rather than the student, because he may have more links, he may have more links to the publications, venues, or something, right? So that's quite easily to understand this. The key is how do you work out the algorithm which really do this? Okay. That means we should not just say, after classification, we do ranking, or after ranking, we do classification. You should design the whole thing in a loop, in a mutually enhanced way. It's like we do rank clustering, right? Rank clustering, you put in the EM loop. Okay, you keep doing expectation maximization. You do the ranking keeps changing. The clustering also center keeps changing, right? So that's a similar idea. Simply says you design the algorithm. These two things, ranking and classification, should be in the same loop. Then they will mutually enhance each other. Okay. What is her design? You can see. At the very beginning, okay, that means the iteration, the number iteration, the first one is 1, the first iteration. Okay. This iteration, you just put the initialization in. Okay. Initialization could be, you can think this one is a paper, or this could be an author or something. These are different objects. Okay. She just used those different shape. Thinking play different roles. One could be author, one could be venue, one could be, paper or something, terms. Then she put different color, means different class label. For example, this could be like a database, this could be data mining, this could be like a machine learning. Suppose you get into different colors. Okay. At the very beginning, the first iteration, you just initialize the label's color because you already have the label. You just pass into the network. Okay. Then once you pass into the network, you are going to weigh your neighbors. Simply says, if you connect it to the database, this class, likely this thing connected to the database will have certain distribution in the database part is higher. Okay. That simply says you are going to do ranking distribution. Obviously, if you are in the center, there are quite a few surrounding databases, directly linked to you. You will have more weight because those distribution, once they start propagating, you get higher one, your weight is higher. So essentially, you do the ranking distribution, propagate the weight. Okay. After that, you will go back, to redo the propagation, redo the ranking. So the general philosophy, you can see this. Initially, you just give remember this last one is the class label. Like this K is a class label. Suppose you have K classes, okay? Then this TX is the type. Type means whether this node is a term, or is a paper, or is a venue, or is an author. Okay, so these are the type. Then this small x is a node. That means the probability of this node, whether it should be red or green or blue, it depends on the type and depends on the links, essentially. You can see it depends on the links. That means at the very beginning, you get this, you propagate to your neighbors. The neighbor, suppose X is your neighbor node, based on different type, based on different class, they have a distribution. Okay, you propagate down there. Okay. Then at the very beginning, T is 1. Okay. But once you go inside, you will start doing the soft classification. You can actually use any classification algorithm in principle. Here, suppose we use Bayesian. Okay. You can say there's a distribution, you can use this Bayesian, you do the classification. Okay. So, but this loop is a soft partitioning of the network because the network originally everything is linked. They have the color is just the neighbor, the original label color. But once you start propagation, the neighborhood get more colors of yours, right? So you actually can see. That means you start softly partitioning this network. That means anything closer to the yellow one is yellowish. Okay. Everything closer to the green one is greenish. You get a certain distribution to the green. Okay. So, but you actually keep doing this. They start doing propagation. Then you run your classification algorithm again and again. Okay. That means that every time, every iteration, you give them a class label, but the class label is a soft one as well. Okay. Okay. And then this class label will make the surrounding one, redo the ranking. Because now you say, oh, this one is database. Okay, the surrounding one actually get more confidence on database. So you redo the ranking, you redo the classification. And here, converge. Converge means the change, your cross iteration, the change is very small. Okay, it's almost no change. Okay, that's the time you can calculate the posterior probability. That means once you say stable, you calculate after this what is the probability of this node. It's 80% database, 20% data mining, or it's 80% machine learning. Okay, so you actually start calculating the posterior probability. Then the one with the maximum posterior probability is the class label. That means if you get 80% machine learning, they will say, oh, this node is machine learning. Okay, so of course, at the end, you may still have something vague right in the middle. For example, you may have some technical terms. You even do not know which one it should be. That's fine. You do have some certain nodes which sit right in the middle, so there's nothing worry about it. Even you get a student said, I did a half on machine learning, half on database. So you cannot make a decision. It's perfect. Okay.
So how do you choose the initial types?
Okay, yeah, it's a good question. The question is, how do you choose initial types? Actually, if you choose some type, this is a very good question, because if you choose, for example, let's take the DBRP, those computer science publication as an example. The type could be term, could be research paper, could be author, could be venue. Okay. If you choose a certain type, okay, for example, you say ICML is machine learning conference. Actually, because ICML actually got lots of papers published there. So if you give the label, say ICML there, you actually save a lot of effort. You think about that. If you say Sigma is database, ICML is machine learning, okay, then bang, you get lots of paper classified in that way or propagated that way. You actually save lots of efforts. But if you take a paper, you say this paper is a database paper. The other paper is machine learning paper. Fine. The paper may use lots of different terms. Some are very pure, some are not so pure. Okay, when you give the label, you will take some more efforts. You may need more labels, okay, to label other nodes and finally propagate it. Plus, okay, even for venue, okay, some venue are very vague. I just give you a simple example, like a CIKM. CIKM called Conference on Information Knowledge Management. They almost take everything. Okay, they take information retrieval, they take database, they take data mining, they take many papers. They call it information knowledge management. You think of it, information related to data, knowledge related to AI. They can take anything. They do have different tracks. You label this one, say this one is information retrieval, IR conference, which actually may not be quite right. Then you'll make a lot of mistakes in your final classification, because the conference itself is a mix. Okay. Yes.
I think my question is, how do you choose which node to give the initial type? Like for your previous example, it would be more useful to label the professor instead of one of the students, since he's more central.
Yeah. Yeah, the question is, my previous example, I labeled the professors instead of students, then I propagated looks quite reasonable, quite good. And once you get conferences or terms or authors, actually the philosophy is similar. Okay, authors could be a very productive, very pure author, like Mike Stonebreaker. Okay, he's a diehard database guy. I mark him as a database, then I got a very good one. But if I mark a student, the first year student, I say this one is database guy. Actually, sometimes you'll take much more effort, and sometimes the result may not be as good. Okay, then the term is the same. For example, I mark a term, say the term called machine learning. I mark this one, say machine learning. maybe it's a good one. Or I say I get a Bayesian network modeling or probabilistic graphic model. I say this one is machine learning. It's fine. But if I got a one, say, high efficiency, I mark this one's database. Itself is very controversial, right? High efficiency could be anything. Then it becomes very hard to mark. That's the reason you want to pick up the marking one. You want to pick up the very valuable one, very pure one to do the marking. Then the result will be better. Actually, I have one PhD student. She just submitted a paper called Active Learning in Heterogeneous Networks. Her game essentially is which node should be picked. Should send it to the oracle, send to the expert to label. Because in the network, if you pick up a wrong node, the node itself is very mixed. You give the expert a label, you're not get a very good result. But if you pick the right label, for example, I pick an ICML or Sigma, I mark it, then one label worth many more. Okay, so there are games on the initialization, and people study it. Okay. Yes.
Yeah. So you mentioned right there that if you had a term such as high efficiency, it might be harder to classify because you can see that in lots of different contexts.
Yes.
But wouldn't it be also a concern that since it appears in so many different papers, that it could also get higher ranking, and that this ranking, for a term is going to be so confusing that you're not really sure where it belongs to. Couldn't that confuse the results?
Yeah, very good point. The point is, I said high efficiency. That one is a vague one. Actually, which term you should pick essentially is based on, if you study, for example, active learning. Active learning means you want to pick up something to ask expert to label, but you want to pick up the minimum one. Okay. Then you probably can see clearly if those terms appear with higher frequency and appear reasonably distinct. That means if you have 5 classes and this term happen to cluster in this one rather than in the other one, like efficiency or scalability may appear very frequent, but it's frequent everywhere, so this becomes hard to do. But if you give me, say, a probability graphic model, suppose it's frequent, but it's only frequent, suppose in machine learning, not so frequent, say, in database, then that could be a good term you want to pick. Like SQL, you pick up, you say, this is database. Then likely, one word, one label worth more, right? Yes? Mm-hmm.
Which doesn't make much sense that higher rank authors should have that higher rank should be associated to affiliation.
Yeah, actually, that's a very good point. It depends on what is the task of your classification. The ranking actually are different. That means in this classification, you should automatically work out what should be the ranking. Okay. What should be ranking usually is once you give the class label, if you found this one is in the center of this class label, okay, then this one should rank high. Actually, currently we are using a very simple one, like partition them into different research fields, like database or data mining or machine learning. So that actually is coincident with your network structure very nicely. But even for this network, just give you a simple example. Suppose you say, I don't want to classify that way. I want to classify the authors as, for example, highly productive authors, highly reputed authors, versus the authors actually is a very low quality authors. Okay, suppose I want to do that, then you know the problem becomes I cannot just based on the network to do this natural partition, because any conference may have some highly ranked authors, or may also occasionally may have some low-ranked authors, or some low-ranked conference may crowd it with low-ranked authors. Okay, so in that sense, your ranking will be different. Okay, then you still can use this network to help you. You just think about this. Okay, the highly ranked authors usually were publishing more papers in the highly ranked venues, right? So you will do different kinds of centering, then different kinds of propagation. You still will get it, but it's not as natural, but the network structure still helps. Okay, but if you are interested in this problem, because this problem is a very interesting problem, my student, PhD student, one of them, she just worked out a paper and assumed there's no directly correspondence with network structures. Because here, the example we give is they really, network structure really help you a lot. Okay, sometimes it may not help that much. Okay, those are very good questions. It is still a big open problem, telling you the truth, to do this heterogeneous network classification in a very powerful way. Remember, classification is a very big field in machine learning, but very few studies on heterogeneous network classification. Okay. Now, we give you another one. You can see the general idea is authority propagation. That means you get highly ranked one. The highly ranked one will have more power to propagate through the networks. Okay. The philosophy is you get this node. Suppose this node is green. You mark as a definite green node. Okay. The green node will start propagating to its surrounding. The surrounding will keep propagating down to the next neighbor, right? So you can see. Then the probability, you can see when we calculate this t times 1, the next iteration, the probability calculation, you can see this is the class, this is the type, this is the class label. Okay. Then you have type and class label, you'll propagate down to this node. This node, the propagation actually is based on these several links. They based on initial one and iterative one. The iterative one is based on the summation of the distribution. It's essentially a weighted average. It's the summation of the surrounding links, their distribution of the classes. So you keep doing this. That's exactly the previous one. You can see the previous one I just used this. Say this one is doing classification iteratively, doing soft partition. The real formula inside is this kind of formula. Okay, it simply says you sum up all the surrounding nodes, okay, based on these links, and then you get the probability keep changing. Okay, so that's the general philosophy. Of course, you can read the paper in the detail. So you probably can see you have within class ranking, and you have the within network ranking. If the network distribution actually corresponding your class distribution nicely, you can partition this network into subnetworks like this. Then this ranking, I mean, essentially is once you do iterative way, you do soft partition for become a soft subnetworks. Okay, and these soft subnetworks will help you to further evaluate who is the center, who has more connections, and then the ranking will be changed. Okay, then change ranking, change class label, change distribution until it becomes stable. Okay, now I will show you the power. Okay, you have to use a real data sets to see why this kind of method will be very powerful. Okay, we actually collected about 20,000, this is 15,000 papers. It's around this. You can see there are 14,000 authors, 14,000 papers, 20 conference, and 8,000 terms. So these are the network will contain only database, data mining, AI, and information retrieval. Okay, these 4 research fields. And we think there are 4 labels like this. Just take these as a class label. Okay. And with this class label, you actually can see the links containing the paper linked to conference, paper linked to author, paper linked to term. That's exactly the star network model. Okay. With this, we actually take a few other algorithms which are very popular in classification. Many of them are network-based or graph-based classification. Like this one is ARGC, was published in NIPS 2003. This one, VWRN, is another one published. These are several very well-known algorithms. Then we want to compare to see, if you give small number of labels. Remember, we know that you can give labels to venues, but that's not very fair. You give a few good venues, you basically get work done. Okay, we want to give other labels to see how the power you can get. Okay, you can see this A means author, this P means paper. We label, that means you got so many papers, so many authors. We pick only this very small number of papers and authors to label them. Then you see how many we picked. This, remember, if you study machine learning algorithm, usually you have a training set, finally you have a test set. Usually a training set is like a 2/3 of training, 1/3 of testing. You actually get a lot of things you want to do training. But in the network, such a big one, you don't want to get too many labels because that's a lot of work. So we only give you 0.1% of the authors, 1.1% of papers, label them. That means within this very large network, you only got, what do we mean 0.1%? You can think about this, okay? You get 14,000 papers. 0.1% means 14, right? It's 1/1,000. That means you pick up 14 papers, you pick up 14 authors, you label them, then you check the whole network, everything, say whether they are labeled. They classify right. Okay, that's a very, very sparse label. You think about this. Then remember there are a total of 4 classes. You can see this one. These several algorithms, no matter they use MetaPath AA, author linked with author, or author linked with conference paper term, their accuracy is around 25%. 25% essentially is a random guess. You think about it. If you take a GRE, you say, I know nothing, I just randomly cross it, you probably get 25%, right? Because the randomly, I do not know. They have 5 choices, you will get 20%. Right, if you randomly cross it. And here you can see you have 4 classes. This is almost a random choice, right? It's not really doing classification. But if you look at others, they can get 40%, not bad, okay? But it's still 40%, you may not like it. So here you can see GNet Mine, her first algorithm got it like 82%. Okay, that's pretty high. But then her second algorithm, rank class, got 83.9%. You can see, even you use very small number of labels, you still get very good result. The reason is you can propagate, you can calculate all the propagations, and you can rank them. And once you rank them, they are more confident, so they carry more weight in the propagation. Usually you will do it quite right. Okay. Let me show you. Actually, one thing I should say is this one is final results on authors, final results on papers, the final results on conferences. You probably say the final result, even you look at the average, you would say they have different classification power. You're just thinking about it. Conferences is somewhat easier to get close to 90%. You can think here. The last several get 90.5, 95. But if you look at the authors and the papers, it's hard to reach even 90%. Why that's the case? Actually, that's a case of data itself. You think about this, okay? If you say this conference is ICML, this conference is SIGMOD, you say ICML is machine learning conference, SIGMOD is database conference, nobody will argue with you, okay? You look at the expert give you a label, and your final label, no question. Okay, no question asked, because they are very pure. They're very, very strong. But if you give me an author or give me a paper, even for human, you will have some controversial thing for these 4 fields. For example, just like me, myself, most people label me maybe data mining, but some people may label me as database because I published lots of papers in database conference. So that's the case. You know, even for paper or author, human will have a hard time to say you give me a pure label, right? So that's the same thing. That's why you probably can see this ranking is inherent on the data itself. It's not like you know, you don't have a capability. The data itself is kind of multi-label. Okay, it's a distribution. That's why it's very hard to get 100%, right? But a very interesting thing is not only you get a pretty good classification result, but you also, as a byproduct, you can get a ranking. Because remember, you are doing ranking on every term, every paper, every author, every conference. Right? You are doing the ranking. So let's look at what is her running, get a classification as a byproduct. What is the ranking she provided? Okay, these 4 research fields. The first thing you can think about are top-ranked conferences. If anybody in the database field, you probably see these VRDB, SIGMOD, ICD, POTS, EDBD. Those are really, really database conference. Okay, and if you are in the information retrieval field, you may find a SIG-IR, ECIR, CIKM, WW, Wisdom, are the IR conferences. Okay, you may give me a little hard time. You say, you said CIKM is a mixture. Why they put into IR? I say it's right. Actually, if you really go down to CIKM, they have probably 50 to 60% papers IR papers, and the other papers are mixture. Okay, to that extent, many people are thinking at least this is a little more IR rather than data mining or database. Okay, but you may also say, I think WW or Wisdom actually rank higher, at least higher than ECIR. Why you put WW rank lower? Okay, actually, if you think about this, this ranking is not just based on, mainly not based on reputation. It's based on the purity. No, if you got more papers, you are more pure, you rank high here. But WW is not so pure. If you go to WW conference, you read the papers. Some are really IR papers, but some are like more like a system, how to implement this. Some are data mining papers. Some actually could be machine learning or something. So WW is mainly IR, but it's a little mixed. So since it's mixed, but the ECIR, SIG-IR, they are more pure IR. That's why you probably can see the ranking itself does tell you, something not bad. But probably the most interesting thing is you look at the terms. The terms actually is very good. You look at we just said IR. You look at the IR, the system pick up the top 5. Say retrieval information, web, search, text. Even suppose you work in the information retrieval field. I ask you to pick out 5 alternative terms to beat this 5. It's very hard for human even. Right? You think about it, these 5 terms are probably really the best terms to categorize IR. Right? So that's the reason you probably can see that's this whole thing, the classification actually it's efficient, but in the meantime, it's really effective and take the ranking as a byproduct as well. The philosophy, the very different philosophy from other classification is we think not every node is identical. You need a ranking, okay? So if anybody study classification algorithm, you probably heard there's a boosting algorithm, quite a famous one called Ada boost. Ada boost general philosophy is they start putting different weights instead of saying everything is identical. They put different weights. The weights is this. Okay, you first round you do the classification. Some label is right, some label is wrong. Okay. The Ada boost, the general philosophy is you take the first time wrongly labeled those samples, those examples. You put more weights in. It's more like you did homework or did a test, you did some question wrong. The next time when you do the review, you put more weights on this wrongly done thing. That means I have to remember the lessons. Okay, you put that one more weights, then the next time you do it, you adjust your classification mechanism. Somehow you do it better. Okay, but that one is still not this philosophy. This philosophy, to some extent, is you put the real right one, the really good one, really center one. You put more ranking. Okay, the philosophy is in the real world, nothing is pure. Okay, since nothing is pure, you put a highly ranked, highly pure one. Higher ranking, your whole model constructed will be better. Okay, so that's a different philosophy, but it works out very nicely. Okay, so this one is in Copenhagen. This is the original was a royal palace. Okay, then now it's converted into a museum, so everybody can get in. You can see we did a classification work. Now I'm going to show you prediction. We call relation prediction. Actually, you probably heard, if you go to the web search or many things, you probably heard link prediction. The link prediction, I think if you play with, say, LinkedIn or Facebook, when you log in, they will say, oh, these are the people likely will be your friends. Okay. They put a friend recommendation, ask you to invite those people to be your friend. Okay. How they do this? They basically say they use the friends of friends could be friends. If you suppose this guy has 3 friends in common with you, likely you could invite him. Maybe you already know him, but or at least somehow you should invite him to be your friends. So they basically based on these, they call link prediction. You have many common neighbors, so then that will be your friends. Okay. But this friendship prediction is based on the homogeneous objects, just based on the friendship links, friends and friends. Okay, how many common neighbors? But in many domains, this may not be quite true. Okay, I remember we had some interview people came, say, predicted the co-authors. Okay, I remember she gave a talk, got a very interesting network, and the philosophy is, if you have you share many co-authors, and this guy likely will be your co-author. Okay, so you just co-authors, or common co-authors becomes co-author. Of course, it does have some merit, but I actually asked interviewees, said, in reality, when you co-author a paper with someone, you mainly look at the co-authors, this link, just because you have several co-authors or common neighbors, you invite him or her to be a co-author. She basically said, no, I definitely don't want to decide my co-author based on the co-author's graph. Okay. I said, what do you determine the co-authors? So we work on the same thing, that's why we become co-authors. That's exactly true. You have to based on heterogeneous network instead of homogeneous network. How many people determine you work on paper finding co-author based on the co-author graph? Probably very few people. right? People actually determine the co-author just because we work on the same thing, we work on the same topic, we share some interest, we work together, that becomes co-authors, right? So it's not just based on homogeneous network. It's mainly based on heterogeneous one, okay? That's why Ijo actually work on this one, says you are going to, no matter you are going to think about you want to get a co-authors, or you want to say, I want to cite these papers, or I want to send to this conference. All these decisions are based on heterogeneous links. Okay. So instead of, say, link prediction, many link prediction is on homogeneous objects. We're thinking about a relationship prediction on the heterogeneous objects. Okay. That means you have to think about it, whether you want to read this book, or you want to cite this paper, or you want to go to this conference. It's based on heterogeneous one. Now we look at how we can do prediction using this heterogeneous information network. Okay. Actually, the heterogeneous information network for research publications is almost carry a lot of information you are interested. Because you think about this, we have a paper published in certain venues, got citation by other papers. We have the author and terms of this paper. So this almost carry a lot of semantic information about your paper, about author who, where they publish and who they are going to collaborate. So this information actually is very, very useful. Then the problem becomes, how do you want to do the prediction? Okay, just give you a simple task. Say, suppose you want to predict the co-authors. Okay, just say, the co-author essentially could be author, paper, author. You think about this. Okay, co-author essentially is author, paper, author. They share the same paper ID. That means they share their names on the same paper. Okay. How do you predict these co-authors? Okay. So to predict this co-author, we need to think about all the other semantic relationships in these heterogeneous networks. That means if I want to predict the two authors share the same paper, okay, I need to think about all the other information, like what's the term of the paper, what it is about, where it's going to or already submit or publish in certain venues, okay, how they cite the other papers, right? Those are all the information you have about the paper. Okay. Then if you think just from the semantic point of view, okay, this graph, you can fold them or unfold them into all the possible semantic relationships. Okay. You think about it, you want to predict the APA, author, paper, author share the same paper. Then you may consider this one is a citation. That means if author got this paper cite the other papers, that's the other paper's author. Okay. Whether you are going to co-author with this paper. Simply says you cite the other guy, whether you are going to co-author with him or her in the future. Okay. Yes or no? Based on your common sense. Unlikely, right? Because I may cite, say, Einstein, okay? So you think I'm going to collaborate with him? It's impossible, right? So the people already passed away many years. So that's the case. You probably see this one does not weigh that much. But how do you know it? Look at data, right? The second one is, if other people cite your paper, you're going to collaborate with him. Yes or no? Probably not quite, right? Your paper may get thousands of citations. Not necessarily you want to collaborate with these 1,000 people. But this one may be okay. See, APVPA means what? This paper published in this venue. The other paper published in the same venue. Okay, suppose we all publish in the same conference. Maybe we meet in the conference, we got a discussion. Maybe we are going to collaborate. Right? That's a possibility at least. Okay. So then you look at this. This is a co-author. This is the co-term. That means if we use lots of terms in common, maybe we're going to co-author, right? So there are lots of factors. But the important thing is you look at those factors, which one is more important, which one is not. Which one I should rely on to make decisions. That becomes the important thing. Okay. Then her general philosophy, that's just another paper. Her general philosophy is these are the important critical semantic paths, or you can say metapaths. But to determine which metapaths will play more role, you just need the training. That means you give me some examples. Those people start collaborating, co-authoring papers. Then I look at the back of the history to see what they have, whether they share common co-authors, or share co-venues, or share co-terms, or cite similar kind of papers, all these kind of things. This one actually represents all the semantic relationships. Then you, based on the data, you determine which relationship will be more critical. Then you are going to use it. You can see what she did. It does. She looked at all these things, and based on the data, to work out a logistic regression model. Okay, essentially is you work out which one plays more role. Okay, I have only 1 minute. Then I will pass it to Ali. Okay, is Ali here? Yes, yes. Okay, that's good. I can just show you a little before I quit. Is based on her analysis. You can see she took those metapaths based on lots of data, built this logistic regression model, then check the p-value. Then you probably can see this e to the power minus something means actually is a 0.00 something, right? So you probably can see these e to the power something, these are 4, she put as 4 star. Okay, that simply says those are very valuable paths she will rely on. Okay, so that's actually it's a very, very good idea to determine which path is important. Then, based on this path, she build up the prediction model. The model actually is magically, she actually predicted the next 5 years, okay, who are going to work with you. The data actually is there because she used 2002 before that data to predict from 2003 to 2009 who will be your new co-authors. You never co-authored before. And the result is amazingly good. Later, the next lecture, I'm going to discuss the details. Okay. Now I'll pass it to Ali. I think this one is your unless you change it. Otherwise,
No,
if you did not change it, that's yours. Okay. So you can wear this one.
thank you.
Yeah, that's good enough.
Yeah. Okay, hello guys, I'm Ali. Today's presentation is going to be in 2 sections. The first section is a nice application of networks in virus propagation and immunization, and the second part would be about random graphs, and we will do some theoretical stuff there. Okay, starting from the first section, so we have, Professor, do we have the MATLAB code here, or? Okay, okay. So I prepared the MATLAB code to show you the demo how it works, but that's fine. So we have a graph which the nodes are the individuals, and then there's a link between 2 individuals if they have the potential to give the virus to each other. So if your parents live in another city and you don't see them that often, there will not be any links between you and your parents because you cannot give the virus through the phone, for example. So, but between any of us would be a link because we all see each other in the class. And then we want to see what is the epidemic threshold for an arbitrary graph. So What I mean by this is that if the virus starts propagating through the network, in which conditions it will die out after some iterations, and all the people in the graph would be healthy, and in which conditions the virus would propagate, and a fraction of people would always be sick in the graph. Okay, the problem setup is like this. As I said, the nodes are individuals, and the social links are put between two individuals if they have the potential to give the virus to each other. And then, for sure, the nature of the virus also has an impact to the problem. So here is just one kind of virus propagation model, which, for example, a person might be in a state S, which is susceptible, he is healthy, and if the neighbors of this person has the virus with beta probability, he gets the virus from his neighbors. And then he goes to infected and infectious state, which he has the virus, and he has the potential to give the virus to his own neighbors. And then with some probability, he gets removed or recovered. What I mean by removed, he may die, and then there would be no threat from his own, from that person to his neighbors. Or he may get recovered, and mumps is a disease that can be modeled with this VPM. And as I said, this VPM depends on the nature of the virus. So there are many different VPMs. Here is another example. You are in susceptible state, and with theta probability, you get to vaccinated state where you have the vaccination and there is no threat for you. But with gamma probability, you lose your immunization, and then you are again in a state S, and with beta probability, you go to a state E, which you are exposed to the virus, and you have the virus in your body, but you cannot give it to other people. But after some time, with epsilon probability, you go to a state I, and you are infected and infectious, and then you get healed with some probability. This is another virus propagation model for some other viruses. So here, just for completeness, I've brought the different state definitions that are widely used in VPMs that I've just talked about, most of them, S, I, R, V, and E. And here are the symbols that are being used in VPMs. I also talked about them. But A, for example, is the adjacency matrix of the network. And N is the number of nodes. And lambda 1 is the largest eigenvalue of the adjacency matrix that will play a big role in what we are going to study. Okay, there are different kinds of VPMs that we have talked about, SIR and SEIV. We are not going to talk about all of them for sure here. But here is the lattice. And SSR, I square, VSR is the most general VPM that all the other VPMs, virus propagation models, are specific examples of SSR, I square, VSR. So we can model all VPMs in the form of many VPMs in the form of SSR, I square, VSR. And SSR, I square, VSR is like this. You are in a susceptible state, and it can have some substates. And then with some probability, you get infected. You go to infected state. And here is the most general VPM that all the other VPMs can be modeled like this. Okay, here is a supermodel theorem. What it says is that for SSR, I square, VSR virus propagation model and any arbitrary undirected graph, the sufficient condition for the system to be stable, what I mean by stable is that the virus dies out after some time. So all people would be healthy after some time. So the sufficient condition for the stability of the network is that the parameter S, which is the strength of the virus, would be less than 1. And the strength of the virus is lambda 1 times a constant, and the constant directly depends on the nature of the virus, and it depends on the VPM, virus propagation model. And as you see, the strength of the
virus both depends on a constant that depends on the virus and depends on the largest eigenvalue of the adjacency matrix of the network. So the network itself plays a big role to giving a strength to the virus or not. Here is the effective strength of the virus for some VPMs. As you can see, lambda 1 is fixed for all of them, but any VPM can have different constants. The constant may or may not be the same for different VPMs. So lambda 1 is a parameter that shows how connected the graph is. So intuitively, if you think if the graph is very connected, the virus has the potential to be propagated to the network and make all people sick. So if the network is connected, the lambda 1 would be large, and if it is not connected, then lambda 1 would be small. Here is some examples for the largest eigenvalue of the network. For example, for chain graph, lambda 1 is approximately around 2. That is not a large number, and the reason is that there are always some nodes that are far away from each other. But for a star, the largest eigenvalue would be greater, and it would be a square root of n minus 1. And the reason is that any two arbitrary nodes would at most be 2 steps far from each other. So it is much easier for the virus to get propagated here other than here. And for click, obviously, it is the most connected network, and the largest eigenvalue would be n minus 1. And it is very easy for the virus to get propagated in this network. And as the lambda 1 is large, you can see that the strength of virus is large. Here are some applications of the virus. Here are some applications of what we have seen up to now. And one is that, for example, just think that you have the network and you have the nature of the virus, and you want to see which nodes should get the vaccination in order that the largest eigenvalue of the network collapses the most. Intuitively, the nodes that have the largest degree should be removed in order that the network becomes disconnected the most. But this is not always the case. For example, just think that we have a big click here and another click here, and there is a single node which has degree 2 and connects these two clicks. If the virus is in one click, it can propagate through that single node with degree 2 to the other click. So that bridge, the terminology is bridge for that node. That bridge can be very effective in propagating the virus through the network. So there are two kinds of nodes that we should pay more attention to them. One is the nodes that have large degrees, and the other one are bridges. There is some good research here. For example, there is a research that studied which nodes should get the immunization first in order that the largest eigenvalue collapses the most. Condition 2, we have a certain amount of vaccination. For example, if we have 1,000 people and we have the network between them, and we can just afford to do the vaccination for 100 people, who those 100 people should be in order that the strength of the virus collapses the most. Okay, another application is modeling the virus, the computer virus as a virus. So here we have the network between all the computers, and we can see which nodes play the most role in propagating the virus through the network, and then we may put some firewall there, and yeah, that's it. Here is some simulation results. In the first figure, you can see the fraction of infected nodes through versus time. So if the strength of the virus is under the threshold, which is 1, if it is under the threshold, the fraction of infected nodes would go to 0 after some time. But if the strength of the virus is over the threshold, there are always some people who are sick in the network. And here is another simulation result which shows the maximum number of infected people versus the strength of the virus. And as you see in the point 1, there is a peak for the maximum number of infected people in the network. Any questions on the first section? Because, okay. So we continue for the second section. It is about random graphs and phase transition. And we want to find the phase transition point that I will tell you what it is. So you all know about Erdos-Renyi random graph model. We have n nodes. Each edge would be in the graph with probability p, and it will not be in the graph with 1 minus p. Here are two examples. The left graph, both graphs have 1,000 nodes, and the parameter p is 10 to the power minus 4 for the first graph, is 10 to the power minus 3 for the second one. As you can see, the first graph with a small p is very disconnected, and most of the nodes are isolated. But for the other graph, as you can see, there is a largest component of the graph which is connected, and the number of nodes in that connected graph is of the order n, which is the number of nodes. So we want to find for which value for PSR. Okay, PSR, we defined PSR to be the phase transition point. And if the probability is less than PSR, the graph would not be that dense. It would have low density, and the average. So we want to let the number of nodes to go to infinity. And then if p is less than PSR, the average size of the of different components of the graph would be finite. So even if n goes to infinity, if p is less than the phase transition point, the average size of different components of the graph would be finite. So you can see that it would be very sparse. And if p is greater than PSR, the graph would always have a largest component which is connected, and it is of the order O(n). Okay, the phase transition point is 1 over the number of nodes, but we are going to just do the mathematical stuff and find this 1 over n. Okay. The PMF for the degree of a node is just a binomial distribution. This is the formula that I have written here from the book, but I think it should be n minus 1, and it should also be n minus 1. I will talk about it, but it doesn't matter because n is going to go to infinity, and n minus 1 are the same approximately. But for every, okay, the PMF for the degree of each node is like this. If we want to have k edges for a node, we have n minus options. So there are n minus 1 choose k options for choosing those k's, and then the probability of those edges to be in the network is p to the power k, and then the other edges should not be in the network, so the probability is 1 minus p to the power n minus 1 minus k. If we use the approximation 1 minus epsilon to the power x is e to the power minus epsilon x, we can write this PMF as z to the power k, e to the power minus z over divided by k factorial. And z is the probability times the number of nodes minus 1. And as you see, this is just the Poisson distribution. So some people call Erdos-Renyi's graph as Poisson graph, Poisson random graph, because the PMF of the degree of each node obeys the Poisson distribution. Okay, we define U to be the probability of a node not belonging to the largest component of the graph. So we randomly choose a node from the graph, and the probability that the node does not belong to the largest component of the graph is u. And as you can see, if a node does not belong to the largest component of the graph, all of its neighbors should not also belong to the largest component of the graph. And the probability that all the neighbors, so this randomly chosen node has k neighbors, and the probability that all k neighbors do not belong to the largest component of the graph would be u to the power k. Okay, starting from the second line, as I said, u is the probability of a randomly chosen node not belonging to the largest component of the graph. We can see, we can have another approach, and as I said before, we can say that all the randomly chosen node has k neighbors, and the probability is pk. And the probability that all the neighbors do not belong to the largest component is u to the power k. And k can be any number from 0 to infinity, because the number of nodes would go to infinity. So I just add them up, and I use the Poisson distribution for pk. I just plug in from the previous slide here. So the formula would be e to the power minus z, the summation of uz to the power k divided by k factorial. K is from 0 to infinity. And this is just the Taylor series for e to the power uz. And then if we simplify this, it would be e to the power z times u minus 1. So u is equal to e to the power z u minus 1. In the next slide, I'm going to define 1 minus u to be s, a new parameter s. So s is 1 minus u, and as you can see here, u is e to the power minus zs. So s is equal to 1 minus u, which is equal to 1 minus e to the power minus zs. And so s is equal to 1 minus e to the power minus zs. If I plot s and also 1 to the power minus e to and also 1 minus e to the power minus zs, then for z less than 1, the only solution would be s equal to 0. So u would be 1. So if I choose if I randomly choose a node with probability 1, that node does not belong to the largest component of the graph. So there would be no largest component of the graph. But if z is greater than 1, there would be a non-zero probability for s, so u would also be greater than 1. So if I choose a random node with some probability, it belongs to the largest component of the graph. So z equal to 1 is a phase transition point. And we defined z to be the probability times n minus 1. So p would be 1 over n minus 1, which is approximately 1 over n that I just talked about it before. So here was the approach to find the phase transition point for the graph. Here are the references that I used. The main was Christos Folotz's book on data mining. I just gone through it and see which parts were not covered in the class, and I just presented here. Thank you.
Yeah, I think the presentation is really good. I believe, because in any class, we always leave some parts not covered. Actually, this part, in the beginning, I introduced you, said that there will be a new textbook by Barabasi, which will be published this year in April. Actually, this virus propagation, dynamics of the graph, is a major part covered as a new stuff, which we did not cover in the class. So it's nice Ali covered here. Okay. So I still strongly recommend more students to sign up, especially for the text mining, those parts. Because there are limited slots. If you considering to present, you should contact me earlier. Okay, thank you.